studying the weather questions on the commercial pilot exam, written exam. So the first question is, which is a direct cause of atmospheric circulation? And that's heat exchange. Heat exchange is a direct cause of atmospheric circulation. What is the standard temperature at 10,000 feet? So on a standard day, sea level, or a standard atmosphere has a standard temperature of 15 degrees Celsius on the surface at sea level, and a standard atmosphere has a temperature lapse rate of 2 degrees Celsius per 1,000 feet. So at 10,000 feet, the temperature has lapsed by 20 degrees Celsius from a starting point of 15 degrees Celsius. So the temperature at 10,000 feet on a standard day is 15 degrees, which is the surface at sea level, minus 20 degrees Celsius. So the answer is -5 Celsius. So 10,000 feet, so it's 2 degrees per 1,000 feet, so 2 times 10 is 20, so it's going to be down by 20 degrees. So if it starts at 15 degrees Celsius on the surface, minus 20, it's going to be -5 Celsius. What is the standard temperature at 20,000 feet? So you would do that minus 15 minus 40, so that would be -25. Which conditions are favorable for the formation of a surface-based temperature inversion? So that happens on clear, cool nights with a calm or light wind. Which conditions are favorable for the formation of a surface-based temperature inversion? That happens on clear, cool nights with a calm or light wind. So basically, surface-based temperature inversions occur on a clear, cool night when the air close to the ground is cooled by the lowering temperature of the ground. The air within a few hundred feet of the surface becomes cooler than the air above it. Frontal inversions occur when warm air spreads over a layer of cooler air, or cooler air is forced under a layer of warmer air. Standard temperature at sea level is 15 degrees Celsius. Given a pressure altitude of 12,000 feet, a true air temperature of 50 degrees Fahrenheit, from the condition given, approximate the density. What is the density altitude? So if you put in the given conditions, so 50 degrees Fahrenheit is 10 degrees Celsius. You can use your E6B, and the answer would be 14,134. So if you don't use the EFB, you can just use this formula to calculate the density altitude. So you put in the pressure altitude of 12,000 feet plus 120 times the outside air temperature minus the standard temperature equals density altitude. So density altitude will equal the pressure altitude, 12,000 feet, plus 120 times the outside air temperature, which is 10 Celsius, minus the standard temperature, which is -9 Celsius. And that gives you a density altitude of 280 feet. So yeah, you just look at the standard temperature at 12,000 feet. So that would be, let's see, at 0 it's 15 degrees, so 12,000 would be times 2, so 24. So 15 minus 24 equals -9, I think. Yes, that's right. -9. And outside air temperature is 50 degrees Fahrenheit, so 10 Celsius. I guess you have to know to calculate that. So it's density altitude equals pressure altitude plus 120 times outside air temperature minus the standard air temperature. And that gives you the density altitude. In fact, I'm going to go ahead and write that down, that formula, because that seems pretty important to know. So density altitude equals pressure altitude plus 120 times outside air temperature minus standard temp in Celsius. Okay, save that. Okay, we go next. Given a pressure altitude of 5,000 feet with a true air temperature of 30 degrees Celsius, it's pretty hot, the density altitude would be, so 5,000 feet plus 120 times outside air temperature of 30, and then at 5,000 feet our standard temperature will be, so that's times 2 equals 10, so 15 minus 10 is 5, so 30 minus 5 is going to be 25 times 120 plus 5,000, so the answer is 8,000 feet. So pretty close to that. Pressure altitude of 6,000 feet, true air temperature of 30 degrees Fahrenheit. What is the density altitude? So 32 Fahrenheit is 0, so you know that 30 Fahrenheit is negative 1.1. I guess we got to figure out how to get that. So density altitude, once again, pressure altitude, so 6,000 feet, plus 120 times this formula, which is outside air temperature, so that's negative 1.1, and then at 6,000 feet, that would be 12, so 6 times 2 is 12, so 15 standard minus 12 is 3, so 1.1 minus 3 times 120 plus 6,000 gives you 5,507 feet. Once again, 7,000 feet, true air temperature is 15 degrees Celsius, density altitude will be pressure altitude 7,000 plus 120 times the outside air temperature was 15, and standard temperature, so it will be 1, because it's 7,000 times 2 is 14, so 15 degrees Celsius minus 14 is going to be 1, so this is the formula right here. Or you guys could use the E6B. But yeah, as long as you can remember the formula. So once again, the formula is for density altitude is pressure altitude plus 120 times outside air temperature minus standard temperature in Celsius only. All right. What causes wind? The answer is pressure differences. So air flows from areas of high pressure into areas of low pressure because air always seeks out lower pressure. The combination of atmospheric pressure differences, Coriolis force, friction, and temperature differences of the air near the Earth cause two kinds of atmospheric motion: convective currents, which is an upward and downward motion, and wind, which is a horizontal motion. Currents and wind are important as they affect takeoff, landing, and cruise flight operations. Most importantly, currents and wind, or atmospheric circulation, cause weather changes. So the answer to what causes wind? Pressure differences. In the northern hemisphere, the wind is deflected to the right by Coriolis force. In the northern hemisphere, the wind is deflected to the right by Coriolis force. So I guess if you're flying to New York from California, it's faster because the wind is, you're going to have a tailwind, typically. So the force created by the rotation of the Earth is known as Coriolis force. This force is not perceptible to humans as they walk around because humans move slowly and travel relatively short distances compared to the size and rotation to the rate of the Earth. However, the Coriolis force significantly affects motion over large distances, such as an air mass or body of water. The Coriolis force deflects air to the right in the northern hemisphere, causing it to follow a curved path instead of a straight line. The amount of deflection differs depending on the latitude. It is the greatest at the poles and diminishes to zero at the equator. The magnitude of Coriolis force also differs with the speed of the moving body. The greater the speed, the greater the deviation. In the northern hemisphere, the rotation of the Earth deflects moving air to the right and changes the general circulation pattern of the air. So to answer the question, in the northern hemisphere, the wind is deflected to the right by Coriolis force. Why does the wind have a tendency to flow parallel to the isobars above the friction level? The answer is because Coriolis force tends to counterbalance the horizontal pressure gradient. So we can see that the upper air wind in the atmosphere above the friction layer, the lowest few thousand feet, only PGF and Coriolis force affect the horizontal motion of air. Remember that the PGF drives the wind and is oriented perpendicular to height contours. When a PGF is first established, the wind begins to blow from higher to lower heights, directly across the contours. However, the instant air begins moving, Coriolis force deflects it to the right. Soon the wind is deflected a full 90 degrees and is parallel to the contours. At this time, Coriolis force exactly balances PGF, as shown in figure 7.8. With the force in balance, the wind will remain parallel to contours. This is called the geostrophic wind. So once again, the question is, why does the wind have a tendency to flow parallel to the isobars above the friction level? So when you get above the friction level, which is the first couple thousand feet above the ground, the Coriolis force tends to counterbalance the horizontal pressure gradient. The wind system associated with the low pressure area in the northern hemisphere is a cyclone and is caused by Coriolis force. As the air tries to blow outward from the high pressure, it is deflected to the right by the Coriolis force. Thus, the wind around a high blows clockwise. The wind around a high blows clockwise. The pressure with its associated wind system is an anticyclone. The high pressure associated with its wind system is an anticyclone. The storms that develop between the high pressure systems are characterized by low pressure. As winds try to blow inward towards the center of low pressure, they are deflected to the right. Thus, the wind around a low is counterclockwise. The wind around a low is counterclockwise. The low pressure and its wind system is a cyclone. Winds blow parallel to isobars, which are contours on the upper level charts. The winds are clockwise around highs and counterclockwise around lows. So around highs, they go counterclockwise. I guess you can remember high is to the right, counterclockwise. And around the lows, it's counterclockwise. So low is like bad, opposite, counterclockwise. High, good, clockwise. So once again, the question is, the wind system associated with a low pressure area in the northern hemisphere is a cyclone and is caused by Coriolis force. So if it's low pressure, it's a cyclone. With regard to wind flow patterns on surface analysis charts, when the isobars are close together, the pressure gradient force is greater and the wind velocities are stronger. What prevents air from flowing directly from high pressure areas to low pressure areas? The only thing that prevents that from happening is the Coriolis force. In the atmosphere above the friction layer, I don't even know what PGF is here when it's saying, but basically air would normally flow directly from high pressure to low pressure areas, but it's prevented by doing that from the Coriolis force. While flying cross country in the northern hemisphere, you experience a continuous left crosswind, which is associated with a major wind system. So if you have a left crosswind, that must mean you're flying south? I don't know. While flying cross-country in the northern hemisphere, you experience a continuous left crosswind, which is associated with a major wind system. This indicates that you are flying toward an area of generally unfavorable weather conditions. So the answer here is, okay, no matter which direction you are flying, which is north, south, east, or west, if you start to fly into a low-pressure system, which of course rotates counterclockwise, otherwise known as cyclonically, you will have a left crosswind. So yeah, if you notice the wind going counterclockwise, you will have a left crosswind. Just imagine a low pressure system rotating to the left, and you're trying to fly into it. Low pressure systems are normally associated with bad weather. So you're flying cross country in the northern hemisphere, you experience a continuous left crosswind. This indicates that you are flying toward an area of generally unfavorable weather conditions. Which is true with respect to high or low pressure system? A high pressure area or ridge is an area of descending air. A high pressure area or ridge is an area of descending air. High pressure systems are generally areas of dry descending air. Good weather is typically associated with high pressure systems for this reason. Conversely, air flows into a low pressure area to replace rising air. This air usually brings increasing cloudiness and precipitation. Thus, bad weather is commonly associated with areas of low pressure. A low pressure area or trough is an area of rising air. A low pressure area or trough is an area of rising air. High pressure systems are generally areas of dry descending air. Good weather is typically associated with high pressure systems for this reason. Conversely, air flows into a low pressure area to replace rising air. This air usually brings increasing cloudiness and precipitation. Thus, bad weather is commonly associated with areas of low pressure. So once again, just remember that a low pressure area or trough is an area of rising air. When flying into a low pressure area in the northern hemisphere, the wind direction and velocity will be from the left and increasing. So no matter which direction you're flying, if you fly into a low pressure system, which of course rotates counterclockwise or cyclonically, you will have a left crosswind. As you first encounter the outer edge of the low, the winds will not be that strong. However, further into the system you fly, the stronger the winds will become as the isobars get closer and closer together. Which is true regarding actual air temperature and dew point temperature spread? The temperature spread decreases as the relative humidity increases. The temperature spread decreases as the relative humidity increases. So the temperature dew point spread, or dew point depression, the difference between an air parcel's temperature and its dew point is the dew point depression, or commonly referred to as the spread. Surface Aviation Weather Reports, or METARs, provide observations of both temperature and dew point. The temperature greatly affects the air parcel's ability to hold water and vapor, while the dew point indicates the actual quantity of water in the parcel. As the spread decreases, relative humidity increases. When the spread decreases to zero, relative humidity is 100% and the air parcel is saturated. So regarding actual air temperature and dew point temperature spread, the temperature spread decreases as the relative humidity increases. The temperature spread decreases as the relative humidity increases. That makes sense because when the dew point goes up, the difference between the actual air temperature and the dew point gets smaller. The general circulation of air associated with a high pressure area in the northern hemisphere is outward, downward, and clockwise. So high pressure areas in the northern hemisphere have outward, downward, and clockwise. So in the northern hemisphere, the flow of air from areas of high to low pressure is deflected to the right and produces a clockwise circulation around an area of high pressure. This is known as anticyclonic circulation. The opposite is true of low pressure areas. The air flows towards a low and is deflected to create a counterclockwise or cyclonic circulation. High pressure systems are generally areas of dry, descending air. Good weather is typically associated with high pressure systems for this reason. Conversely, air flows into a low pressure area to replace rising air. This air usually brings increasing cloudiness and precipitation. Thus, bad weather is commonly associated with areas of low pressure. Virga is best described as streamers of precipitation trailing beneath clouds, which evaporates before reaching the ground. Virga are wisps or streaks of water or ice particles falling out of a cloud, but vaporizing before reaching the Earth's surface as precipitation. So virga is just streamers of precipitation that never hit the ground. Moisture is added to air by evaporation and sublimation. Moisture is added to the air by evaporation and sublimation. Water is present in three states: liquid, solid, and gas. All three forms can readily change to another, and all are present within the temperature regions of the atmosphere. As water changes from one state to another, an exchange of heat takes place. These changes occur through the process of evaporation, sublimation, condensation, deposition, melting, or freezing. However, water vapor is added into the atmosphere only by the process of evaporation and sublimation. Ice pellets encountered during flight normally are evidence that a warm front is about to pass. So if you encounter ice pellets during flight, it is evidence that a warm front is about to pass. Shallow frontal surfaces tend to give extensive cloudiness with large precipitation areas. However, widespread precipitation associated with gradual sloping front often causes low stratus and fog. In this case, the rain raises the humidity of the cold air to saturation. This and related effects may produce low ceiling and poor visibility over thousands of square miles. If temperature of the cold air near the surface is below freezing, but the warmer air aloft is above freezing, precipitation falls as freezing rain or ice pellets. However, if temperature of the warmer air aloft is well below freezing, precipitation forms as snow. So, if you experience ice pellets during flight, it's evidence that a warm front is about to pass. So the rain raises the humidity of the cold air to saturation. This produces a low ceiling, poor visibility, and if temperature of the cold air near the surface is below freezing, but the warmer air aloft is above freezing, rain can fall, and then it can then freeze in the cold air as ice pellets. However, if the temperature of the warmer air aloft is below freezing, it forms as snow because the water, it'll start raining, and then the temperature of the water, I guess if the temperature of the warmer air aloft is well below freezing, then precipitation forms as snow. What is indicated if ice pellets are encountered at 8,000 feet? This is freezing rain at a higher altitude. A favored location for severe clear icing is freezing rain and/or freezing drizzle. Rain forms above the frontal surface at temperatures warmer than freezing. Subsequently, if it falls through air at temperatures below freezing, it becomes supercooled. They freeze on impact with an aircraft. If the below freezing layer is shallow, freezing rain will occur at the surface. If the below freezing layer is deep, the supercooled droplets may freeze into ice pellets. Ice pellets indicate icing above. The icing can be severe because of the large amount of supercooled water. Icing and freezing precipitation is especially dangerous because it often extends horizontally over a broad area, and a pilot may be unable to escape it by descending to a lower altitude. Ice pellets encountered during flight are normally evidence that freezing rain exists at higher altitudes. When conditionally unstable air with high moisture and very warm surface temperatures forecast, one can expect what type of weather? So you have unstable air that's high in moisture and very warm surface temperature. You can expect strong updrafts and cumulonimbus clouds. So this is just basically everything you need to create a thunderstorm. Water vapor, unstable air, and lifting mechanism. What is the appropriate base of cumulus clouds if the temperature at 2,000 feet MSL is 10 degrees Celsius and the dew point is 1 Celsius? So the difference between the temperature and the dew point in this question is 9 degrees. So 10 degrees Celsius and the dew point is 1, so that's 9. So divide the temperature difference by the convergence rate of 2.45. So 9 divided by 2.545 equals 3.67 thousandths of feet. So the temperature and dew point will converge at 3,670 feet. So the actual altitude will be 3,670 feet plus 2,000, which is here. So that's 5,670 feet. So that's the closest answer, I guess. 6,000. If clouds form as a result of very stable moist air being forced to ascend a mountain slope, the clouds will be stratus type with little vertical development and little or no turbulence. If clouds form as a result of very stable moist air being forced to ascend a mountain slope, the clouds will be stratus type with little vertical development and little or no turbulence. So yeah, because when stable air is forced upward, the air tends to retain a horizontal flow, and cloudiness is flat and stratified. Stratiform clouds indicate stable air. Flight generally will be smooth, but low ceiling and visibility might require IFR. So if clouds form as a result of very stable moist air being forced up a mountain slope, the clouds will be stratus type. So that's kind of like level, with little vertical development and or little or no turbulence. What determines the structure or type of clouds which will form as a result of air being forced to ascend? So yeah, basically if the stability of the air is unstable, it'll be more like cumulus clouds. And if it's stable, then it'll be stratus type. So basically the key factor is the stability of the air before lifting occurs. Refer to the excerpt from the following METAR. At approximately what altitude AJL said bases of convective type So I guess you just look at the dew point spread and the temperature. So over here, we look at, I think it's 26 and 4. So 26 degrees Celsius and 4, that's 22 degrees difference. So 22 divided by 2.45 equals 8.98 thousand. So just got to remember that formula. I'm going to write that down too. So height of cloud base. All right. Okay. Height of cloud base equals temp minus dew point divided by 2.45. This is in Celsius. So if the temperature is 22 degrees, or so the temperature is 26 and the dew point is 4 degrees, so 26 minus 4 is 22, so you divide 22 by 2.45. Okay. What are the characteristics of stable air? Poor visibility, steady precipitation, and stratus clouds. I think we'll end there.